Hello, everyone. Good morning. It's my pleasure to introduce our work, Nomad, non-exclusive memory tiering via transactional page migration. This is a joint work between the University of Texas and Intel Labs. As new memory devices such as HBM, CXL-based memory, persistent memory, and storage class memory continues to emerge, the future memory hierarchy will consist of diverse memory devices with distinct characteristics differing in speed, size, cost, scalability, and persistence. The new memory hierarchy are all byte-addressable by CPU via ordinary load and store instructions, and the performance gap between the tiers are getting narrower. Central to managing such a tiered memory system is the page management in the operating system. Modern Linux kernel manage new memory devices through numerous interfaces. In a typical configuration with 6 memory or persistent memory, we may have a performance tier with DRAM connected to CPU through DDR4 or DDR5 protocol. The performance tier features a high per gigabyte price, high performance, and limited capacity. And the capacity tier appears to be a CPU-less memory node with a lower per gigabyte price, lower performance, and much higher capacity. Traditionally, the operating system employs inclusive caching to manage data between the DRAM and disks. Given the several orders of magnitude performance gap and the disks are not directly accessible by the CPU, the fast memory is usually used as a cache of the slow tier. Therefore, the hit rate of the performance tier is paramount to overall performance. In the new memory hierarchy with the tiered memory, because the performance and the capacity gaps are much narrower, the Linux operating system employs exclusive tiering to manage the data between the capacity tier and the performance tier. Exclusive tiering ensures that a specific page only resides on one of the tiers and has low pages on other tiers. Exclusive tiering relies on page migration to move the hard data to the performance tier and cold data to the capacity tier. Although exclusive tiering maximizes memory utilization, it incurs a high migration cost and may not lead to overall good performance. To demonstrate this problem, we evaluate transparent page placement, the state-of-the-art memory tiering approach in Linux, which is also based on exclusive tiering. We created a synthetic workload that follows a zip-fin access pattern. The workload's working set size fits in the performance tier, but was initially placed in the capacity tier. We measured the bandwidth when the hard data was being migrated, and the fast tier when the page relocation was completed. We also disabled the page migration and used it as a baseline. As shown in the figure, although TPP was able to eventually move all the hard data to the fast tier and achieve the 30% higher bandwidth compared to no migration, it incurred prohibitively high overhead during page migration and led to 16 times bandwidth loss. Next, we review the state of the art and motivate our work. There are 2 issues to be addressed in the tiered memory management. The first issue is memory access tracking to decide which data is hot. And the second issue is an efficient management mechanism for page migration. The page fault-based access tracking leverages the existing LRU-based page replacement algorithm in Linux to determine page hotlists. Representative work approaches include AutoNuma and TPP. Page fault-based tracking marks all pages in the slow memory as protected and invokes a hint or minor page fault on every access to these pages. If a page is deemed hot and in active LRU list, it is migrated to the fast tier. Page fault-based tracking is accurate as it evaluates every page on slow memory for potential migration, but incurs high overhead due to frequent page faults. The minor page faults also disrupt normal program execution and the critical path of the user's data access. Another approach is page table scanning. A separate kernel thread periodically scans the access bit of the page table entries to determine hot pages. While it is off the critical path of data user access, page table scanning is to address a difficult trade-off between the scanning interval and the tracking accuracy. Frequent and large-scale scanning yields good accuracy, but that is expensive. Hardware-assisted tracking leverages hardware performance events, such as PBS on Intel processors, to sample events that can be used to infer recently accessed page addresses. Like page table scanning, hardware sampling can be lightweight but undermines the tracking accuracy. Depending on how page migration is done, it can be classified as synchronous migration and asynchronous migration. Accurate access tracking, such as page fault-based tracking, is usually followed by synchronous page migration, while asynchronous page migration can be used for page table scanning and hardware sampling, since they are done by a separate kernel thread. So, our question is, can the tiered memory be both accurate and lightweight? In this paper, we propose Nomad, a more efficient tiered memory management scheme that seeks to minimize the overhead of page migration and move page migration off the critical path of users' data access. Nomad embraces a non-exclusive memory tiering policy to prevent memory thrashing when under memory pressure. Unlike existing page management schemes that move pages between tiers and requires that a page is only present on one tier, Nomad instead copies pages from the slow tier to the fast tier and keeps a shadow copy of the migrated pages. The benefit of Nomad is to avoid unnecessary page migrations when fast memory is under pressure. Central to Nomad's design, there are two key mechanisms, transactional page migration and page table scanning. Note that Nomad is a page fault-based management approach and is orthogonal to the existing works. The key idea of transactional migration is to keep pages accessible during migration and treat the migration process as a transaction. It opportunistically copies the page to the fast tier where the page can be accessed by users. Migration is committed if the page copied was not updated. Otherwise, the migration transaction is aborted and will be tried later. TPM involves the following steps. First, TPM saves the original value of the dirty bit in a page's PTE to clear it for the migration. If the dirty bit is set during migration, the transaction is aborted. TPM issues a TLB shutdown to cover two cores that ever access this page and ensure that subsequent writes to the page will be recorded in the PTE. Note that the page remains accessible and is still mapped to the source location in slow memory. Second, TPM copies the content of the page to the destination fast memory. Third, after the page copying is completed, TPM unmaps the page from the page table and issues another TLB shutdown. After that, the page becomes inaccessible until it's remapped. Next, TPM checks if the dirty bit is clean. If so, the page is remapped to a destination location in the fast memory and the transaction is committed. If the dirty bit is ever set during the migration, the transaction is aborted and the page is remapped back to the source location in the slow memory. The original dirty bit is also restored. Compared to page migration in Linux, TPM significantly shortens the period during which a page is inaccessible. Although transactional page migration takes page copying over the critical path of program execution, it still relies on frequent page faults, up to 15 faults per page, to promote a page from the slow memory to fast memory. Please refer to our paper for more details about the limitations of memory access tracking in Linux. Unlike TPP, Nomad makes a migration decision for each page accessed from slow memory via trapping to minor page faults. Unlike TPP, which only promotes a page residing on the active LRU list, Nomad queues any accessed pages, whether cold or hot, to a promotion candidate queue using exactly one page fault per page. Later, on every subsequent page fault on the other pages, Nomad scans the PTE of pages queued to the PC queue to determine the hot pages and promotes them to a migration pending queue, where transactional page migrations are performed asynchronously by a kernel thread called kpromote. This two-queue design ensures that no page in slow memory goes through the repeated page faults to be promoted. Most importantly, after the initial page fault that adds a page to the promotion candidate queue, Nomad allows the user to freely access the page while a migration decision is made without incurring more than one page fault per page. Nomad introduces a page shadowing mechanism to allow a subset of pages residing in the performance tier to have a shadow copy in the capacity tier. Only pages promoted from the slow tier have shadow copies, and the shadow pages plays a crucial role in minimizing the overhead of page migration during periods of memory pressure. Instead of swapping hot and cold pages between the memory tiers, the page shadowing enables efficient page demotion. As shown in this figure, after a page is promoted to DRAM, Nomad builds a key value store to map between the master page in DRAM and the shadow copy in the CXL or PMEM. The biggest challenge is to track if there are any updates to the master pages so that the corresponding shadow pages should be invalidated. To track updates to master pages, Nomad sets all pages in the first tier which have shadow copies to be read-only, and uses a shadow read-write bit in the page table entry to record the original read-write permission of the master page. As shown in this figure, whenever a master page is updated, a write violation page fault is invoked to handle the invalidation of corresponding shadow page. After the shadow copy is discarded, Nomad restores the original read-write permission of the master page from a software shadow read-write bit, after which the master page can be updated as usual. The potential overhead of page shadowing is the additional write violation page fault, but it avoids unnecessary page swapping when under memory pressure or during page memory thrashing. We evaluated Nomad on 3 of the testbeds: a tiered memory system consisting of DRAM and Intel Optane persistent memory, a prototype system with Intel FPGA-based 6 memory, and an AMD system with a pre-market Micron 6-cell memory. We compared the Nomad with 2 representative works, TPP and MEMTIS. More details of the hardware and software configurations can be found in our paper. We first designed micro benchmarks to evaluate the effectiveness and limitations of the page migrations. The micro benchmarks were configured with 2 types of memory footprints. Resident size is the total size of the memory occupied by a program, and the working set size is the amount of hot memory a program uses during execution. Ideally, effective tiered memory management should bring a small working set size entirely to the fast memory and achieve close to DRAM performance while incurring graceful performance degradation if the working set cannot fit in the fast memory. We also measured performance in 2 graphs. Migration in progress measures the performance when the pages are being actively migrated, and the migration stable is when the system reaches a stable state and most hot data should be migrated to the fast memory. We have observed important trade-offs between Nomad, TPP, and MEMTIS. First, the results show that Nomad is a more effective and efficient approach than the state-of-the-art TPP. It consistently and significantly outperforms TPP in almost all tasks during active migration or memory thrashing. Nomad's transactional migration and page shadowing significantly reduces migration overhead and achieves graceful slowdown under extreme memory pressure. Second, the sampling-based approach MEMTIS fails to effectively capture all hot pages and achieves suboptimal performance when the fast memory can accommodate hot data. On the other hand, MEMTIS incurs much fewer migrations and inadvertently achieves high performance during thrashing. Third, Nomad is more effective for read-only workloads and suffers from migration abortions for write-intensive workloads. Please see our paper for more details, the results on more test beds. Next, we use the latency of the micro benchmark to compare the performance of sampling-based and page fault-based approaches. Although the sampling-based approach maintains high throughput during thrashing in the previous test, thanks to a lack of migrations, its latency is suboptimal, suggesting that its page migration is not effective. For more results on real applications, please refer to our paper. In conclusion, Nomad is a tiered memory management mechanism that features transactional page migration, page shadowing, and non-exclusive memory tiering. The result shows that Nomad is significantly more efficient than state-of-the-art management scheme in Linux, but calls for more research on the optimal strategy to enable or disable page migrations under high memory pressure. Thank you.